for this meeting in this location. So, what I'll talk today about will be very similar to those who have heard of what Sergey told you probably in November, I think, in your meeting. Hopefully, I'll be able to give slightly more detail and tell you something about data, which is the most interesting part. So, just to be clear, this is work in progress with several people in this collaboration: Sergey Dubovsky, Guznam is also here, Sasha Moni, and Shantrad Sara. And as some of you might know, this work also builds on previous works, in particular relevant works by Simon Erlenman and Ian Swanson that I will not use explicitly, but to the extent that those work push, we agree with them. So there is nothing new, but hopefully nothing different, but hopefully something new. Okay, so since this is the first talk, I'll start saying something that probably all people in this collaboration know, which is the QCD string, essentially. How do we think of the QCD string? So, okay, so we probably all of you know the story from Toft or Polyakov, or why Yamil should have a dual string theory. But I like to emphasize the viewpoint that Victor and Sergey and Raphael emphasize in their paper, which if you're in effective field theory, how would you discover that there is a potentially dual string or fundamental string in Yamil's theory? Well, what would you do? You start by taking Yamil's theory with zero or small amount of matter, and then you put a quark and anti-quark heavy on the lattice, and you look at essentially at the chromodynamic field, and you see that it localizes on a flux tube of length L and thickness, which is parametrically set by the only scale of the theory, which is the inverse mass of the first group. Okay, so far there are many theories of string-like objects, like cosmic strings or superconductors. So what is special about this? Well, what is special is that, if you have a generic theory like a cosmic string, and you start scattering excitation on this cosmic string, at some point you will have enough energy, and you will produce an object in the bulk. This excitation will produce a star, something in the space. Here instead, what happens is that even if you scatter super high energy states, if the number of colors is large enough, the S matrix on the 2D string is unitary. So this is why you would start to think of this object as a more fundamental object. And in fact, in other words, if you take the limit NC to infinity first, then this long string sector is completely well defined. I haven't told you anything about short strings. Okay, so it's fair to say a lot of the collaboration here wants to understand this string, even just this long string at a non-perturbative level. There are tons of words. We will hear about them. There is most of our understanding still comes from lattice. There is exciting work from the bootstrap, like from the and Victor, and there are several works in 2D. Okay. So still, it's fair to say most of our understanding of this string comes from effective field theory. Guess again, you're probably most of you familiar, but let me just refresh. If you're not, you can ask. So effective field theory is just the idea, of course, that if you have a long string object, this long string object simply is realizing nonlinearly a certain symmetry breaking pattern, as you all know. And the symmetry breaking pattern is that from the d-dimensional Poincare group to the two-dimensional Poincare group transverse rotations. In this language, as you know, we think of the string as the string coordinate as two embedding coordinates. They take tau and sigma. These are the worldsheet coordinates, and I take them to be dimensionless for normalization reason. So L is the length of the string up front here. And xi is that the transverse coordinates are the d minus 2 Golson boson associated with this symmetry breaking pattern. And now, okay, the action is fixed by the nonlinearization of the symmetry. Because probably most of you are used to work probably with Polyakov formalism, but for the purpose of effective field theory, it's often more convenient to work directly in Nambu-Goto, because we will not solve exactly the theory, so it's better to have a formalism where I can get fixed from start my construction and do calculations, so I don't have to deal with all the constraints. Just a matter of convenience, of course. So the action, you all know it, you start with the Nambu-Goto action. This is the leading order derivative action, and this is just the induced metric on the worldsheet. And then you have higher derivative terms. It turns out that they start a fourth order derivative, and they can all be written, as far as I know, in terms of the extrinsic curvature or derivative thereof. Extrinsic curvature has a geometric meaning, but again, if you just effective field theory, it's just derivatives of your field, second derivative of your field. So it's a very normal way to do an effective field theory. You write an action in terms of higher derivatives. And then you have higher derivative coefficient.
Yes, in d equals to 3 or in generic?
Yeah, so here the coefficient is unique in d equal to 3. In d equal 4, I think there's an extra. So, but I'll be talking both about d equal 3 and d equal 4, so I won't be using really this higher degree operator. And okay, so again, many people try to understand the lattice data in terms of this effective string theory, and it was realized soon enough that the modes of this long string, so in d equal 3, there is a unique Colston boson, and this seems enough to at least qualitatively characterize all the states we observe in the lattice in this long string sector. In d equal 4, it was soon realized that actually there is an extra mode on the string, and it turns out that this is a pseudoscalar. It is rather heavy, it's mass 0.75 in units of the string length. Notice that we put a factor here, so this is just that, so this is really alpha prime, this is LS minus 1. And it has a width which is roughly 20%. I think as Andrea Victor showed, probably our best understanding now of this mode, and this is sort of pretty much like the rho unitarizes the pion scattering. I think this mode seems to play a similar role here. And it's very interesting to understand why it's there, but let's say experimentally we know this mode is there. These are data for NC equal 3, but I think for NC equal to infinity they do not change too much. This becomes like 0.6, and this is still 20%, I think. Yes?
What's the rough dictionary between L string and the coupling constant in the gauge theory?
Well, L string is roughly the mass of the first global, which is the lambda QCD. One over, I think it's inverse of lambda QCD.
It's the one, yeah.
So if this was non-Mugoto theory, your first massive state would be at alpha prime. Since it's not non-Mugoto, it's roughly expected to be there. In fact, we know that the mass of the first global in d equal 3 and c to infinity is like 1.6 in these units, and in d equal 4 is roughly 1.2 or 3.
Thanks.
Okay, so this is not the topic of my talk.
If it's not the topic, well, I just wanted to make sure.
Yes.
So here you took Nambugoto, you gauge fixed in some,
Yes.
okay, and you do some expansion, and the claim is, okay, the next claim was what about the pseudoscalar? Like this mode arises how? Or?
So no, I'm just saying, so this is, okay, I'm just saying like, this is effective string theory, and now there are some couplings, as was asked, LS, alpha 0, these are measured from the lattice, we know them in this in the equal 3 from the lattice. Okay. In the equal 4, in trying to do this measurement, people realized that this action wasn't quite complete in a sense, in the sense that there is a pseudoscalar which is pretty heavy in cutoff units, but it's still pretty visible on the lattice. Okay. And so this is really, this is a status, if you want, of what we know for effective string theory from measurement. And we know that there is, I would say this particle is part of our knowledge in this sense.
Sorry for my ignorance. When you say lattice, you mean putting this on the lattice or putting the dual?
Putting Wilson line in the fundamental and anti-Wilson in the anti-fundamental on the lattice, separate them far apart and looking at putting a Purifour group more precisely.
Okay, and that connects
to
the
Young Mills on the
Young Mills. So this is data from Young data, so say from Young Mills.
Yeah, fair. Okay.
Yeah, so we don't simulate this action, of course. Well, I think some people do, but that's not what I mean. Okay, so this is the story so far. Okay, so now we know, as I said, quite a bit about this string, at least numerically. So the question is, can we start using this data that people have measured to analyze the spectrum of the theory? So of course this is, there should be so of course this is an old question. I think it's how string theory started, as you all know. But the point is that since we have understood, I would like to say now, more than in the past about this long string, it seems a good time to revisit this old question. Okay, and where do we start? Again, we start from effective field theory, and we start from rotating strings. So the first entry of the dictionary, you all know it, is that mesons are open strings with quark and antiquark at the endpoint, and glue balls are closed strings. So when do we expect EFT to apply? EFT can only apply when the string is longer than the cutoff scale. And then we use, of course, by relativistic kinematics, we know that this happens when the angular momentum of the particle is large. So we think of a meson, for instance, a rotating string of length L. The length goes like 1 over the angular velocity, and the angular momentum goes like 1 over the angular velocity squared. So from here you immediately see that L is proportional to Ls times square root of j. So you see the parametric separation between the infrared scale and UV scale when j is large. This is a famous fact, and so I shouldn't stand here, I was told. And in fact, if you just take Nambu-Goto action, which is your leading Gaussian derivative action, and you try to push this logic, you predict immediately the Regge trajectory where the mass square is proportional to J in almost straight lines. And at this point, you would immediately declare success, because as you all know, people in the 70s drew this conclusion, look at the plots of the rho, or the pi, say this is isospin equal 1, and they lie on almost straight trajectories. We observed string in the real world. Great.
So what is this mass?
This is the mass of this is the rho, and these are the other particles in the trajectory called rho and A. I don't know. These are the lowest mass particle at fixed angular momentum J. This is the next lowest mass particle at fixed angular momentum J, and isospin equal 1.
So this is a mass for the meson?
Yes, Meson. Okay. Yeah, so this is a schematic of real world data. I'll show you a more precise plot later. But okay, so if you want to go one extra step, then you would ask, okay, can I predict this gap from effective field theory? Or can I understand the quantum numbers of these states from effective field theory? In fact, there are many more. So you want to push further. You don't want to stop at the qualitative observation. We have straight Regge trajectories. So, okay. And that's roughly the motivation of my talk. So are there questions so far? So,
Very quick question. If you fix spin and you start exciting the string radially,
yes.
and you go to large radial excitation number, is there an expectation? How does the spectrum look?
Well, no. I mean, it's clearly not an operation within EFT because you go. But again, there are some ideas, I think, from Victor and others that the UV behavior of the string should be somewhat related to connected integrability. Literally, like the asymptotic freedom means that really the very high energy state in the string behaves in some sense in some integrable way. So one, if you want, long-term motivation would be understanding. Okay, you would like to have some understanding close to reading the trajectory, and maybe hopefully some understanding very far away. But I would say it's very far from what we are able to understand so far. It's a great question. We don't know.
So there are sort of many radial excitations. You mean you have in mind some particular form of radial excitation where you can get something simple?
Yeah.
But what would be like, I guess, what type of radial excitation?
I guess in the case of conformal flux, there are these radial excitations which correspond to these folded strings which probe the horizon. And I don't know if you have some confining background and you imagine a string and you start exciting it radially such that the string approaches the horizon. Maybe there is something.
So then it's like radial in ADS.
Yeah, radial in ADS. Yes, radial in ADS.
So this would be like exciting the dilaton would be on the string or something. Here there is no dilaton or not.
Not necessarily, right? You can have a string and it's an object, and you can perturb it in any direction, right? So the one he's mentioned is an excitation in the radial direction of ADS.
Here the first question we have no
point would look like a dilaton. I'm saying this.
Yeah, but here the first kind of trouble with reproducing, finding analogy of that is that we don't see any sign of radial direction here whatsoever, right? But, there could be some other types of excitations that somehow we get a simple one, but not as we know.
So there is a problem when you try to do EFT as long as you try to do any calculation with the action I showed. And the problem is that if you work with strict Nambu-Goto, these endpoints are moving at the speed of light, which means that I'll show in a moment that the induced metric at the endpoints is singular, obviously. Or here in this case, the case of closed strings, the problem is analogous, but it's even more apparent because the closed string, the rotating closed string solution has two cusps at the location of, at these two singularities. And you can, please, let me see. So let me review more.
So in those cusps, the effective field theory you are writing there, the higher order terms, they become more and more important.
Yes, I'll show in detail in a moment, but yes. So that's precisely the problem. So I should say this problem was already addressed to a large extent by Simon Ellerman, but I want to review it also to show, I think, slightly different solution. So this is the background, or the rotating background. Now it's different than the Austrian background. I work again in dimensionless coordinates, that's why the angular velocity appears as bronze. And but if you rescale time, you just see this is the angular velocity. Alpha f is a free parameter, so I claim that this background is a solution to the equation of motion of the rotating string to all ordering derivatives up to this free parameter, which depends on the boundary conditions. And I chose it such that this is the velocity of the quark. So I'm doing open string. I think we believe at this stage that what we are doing generalizes rather easily to closed strings. You can ask me more later, or I can give you some good comments. So you see that this is the induced metric. You see when alpha f is 1, there is a singularity at sigma equal 1. So sigma is the length coordinate of the string, is between -1 and 1. So in Namugoto action, we find alpha f equal 1, and the well-known result I mentioned before. But okay, so let me just write it. Consider a generic operator, higher derivative operator, you add it to the string, and you use this background with alpha f equal 1, it's because you start from Namugoto, you find that this becomes actually singular. In the sense that in the bulk, the contribution of this operator is small, just plug the solution, you see it's proportional to a large power of omega, so this is small, but it's not integrable because it has singularities at the endpoints. So here I'm really computing the contribution to the classical action, but what this means is that if I compute the contribution of this operator to the mass or the angular momentum of the particle, this will be infinite, and therefore there's a problem for effective field theory. And this is infinite because, of course, there is an integral which I cannot compute. Okay, so at this stage, again, we shouldn't be too worried.
Why are the endpoints moving sort of at the speed of light? There's no mass.
So I'm going to address that in a moment, but if you just use Namugoto action, then you don't add any mass at the endpoint. So, but anyhow, this is exactly the natural objection that I would expect at this point. So you might try and say, okay, in QCD the quarks are not massless, or it's not my right to assume that the quark is massless in effective field theory. I have to give it a mass, and this mass will be naturally of order of the unique scale of the theory, which is lambda QCD. For light quarks, of course. The whole problem is with light quarks. You can ask me about honey quarks, but that's actually straightforward. Okay, so let's add endpoints. Let's add some mass at the endpoints. Let me just write schematically. X dot square at sigma equal 1 and sigma n minus 1. So we add this endpoint term, and we assume this term to be of order 1 over ls, this natural scale. Of course, here now the quarks do not move to the speed of light, but still for large angular momentum, so small omega, they move very close to the speed of light, so the correction is small. So now that integral is calculable, but still you find that that contribution leads to, okay, so let me just write the formula, I'll tell you. Okay, so now you add this term, now you can compute everything, but you still find that it doesn't matter how I order in derivative a term I write, to any derivative, they all contribute to the same order in J, in part here to the leading radial trajectory, all to order J to the 1/4, with some leading contribution suppressed by square root of J. So you're still not happy because you still don't have an organizational principle for all these operators. But okay, if you really care only about the leading radial trajectory, you could conclude, okay, I cannot compute this coefficient, but this is my ignorance and this is my correction to the leading radial trajectory.
Sorry, can you briefly explain why k to the power n gives you the nth radial trajectory?
I'm just saying, like, you add so this is just, I'm just saying this is the contribution to the mass of the leading radial trajectory that you obtain by including the correction from the operator to your action, using this mass term to make sure that the singularity is smoothed out. Okay, so the picture here, I think it's okay, let me just go to another blackboard. Okay, so this is the review of the problem. And of course the problem has a solution.
Gabriel, can I ask another question? So here, if I understand correctly, you are plugging your classical solution to this curvature term. But since you add this extra curvature term, is it possible you can modify the classical solution a little bit to, for example?
So I'm a bit lying. So what happens is that in a sense, once you add this term, this also back reacts on you. So that the right statement is that it doesn't matter what you do if you don't think further than just adding a mass term and naively computing, you'll find that all operators will contribute to order J to the 1/4. Also by accounting of the back reaction that you're asking and all the things.
Okay.
Still like, and of course this also, the real problem of course starts when you want to compute the energy of daughter trajectories. In that case, you want to know whether this is this calculable, this term, the correction here, is this correlated to the correction of the daughter trajectories? I mean, you want to know what is your ignorance on this term. It's 1, 2, 3 coefficients, infinitely many. At this stage you would include infinitely many, but of course that's not the answer.
Is this also the result that you get if you just try to naively regulate this integral and introduce some local counter term to cancel
Well, depends how
that?
you regulate it. I would argue that if you regulate in a way which preserves the symmetry, that's probably what you're going to get. Yeah, I mean, I think that I'm going to explain the physics of this J to the 1/4 in a moment, and then it's going to be completely obvious. I'm just, I would say that if you're smart, you're going to estimate the J to the 1/4 without doing calculations. This is the question. But the point is that you don't want to be smart. You want to be able to hand this problem to an undergrad. Okay, so. Okay, so this is the review of the problem. I'm sorry, I know that many of you know this problem, but I like to. Yeah. Okay. So the basic picture, of course, that this is telling you, is that really you cannot think of the rotating string with 2 point particles at the endpoint. In effective field theory, these point particles come embedded with some ignorance, which is roughly their thickness. Okay? So this is like the effective field theory of black holes. You don't anymore resolve the singularity, whatever. You just know that there is some object with some thickness delta, which is much smaller than what you're interested in. So varying this thickness, you renormalize So as it was already hinted, once you accept that you are not really seeing the point particles, you accept that you should have an effective field theory for this object. It will come with a cutoff, and as you change this cutoff, you will renormalize the boundary action. So these divergences are really an artifact of the fact that you have some rounding Wilson coefficients at the boundary. The thing which is interesting of this problem, and this, is that there is a non-trivial redshift effect between the bulk of the string at the endpoints. The thing which makes this problem a bit different than similar problems is that these objects are moving close to the speed of light. So even if you cut off this object at a distance, some size, roughly inverse lambda QCD scale, the proper time here and the proper time here are very different. So this means that the proper time at the endpoint is roughly, let me just be schematic, of course it's square root 1 minus the velocity, the proper time in the bulk, and this is roughly a factor of square root of Ls omega. Or if you want, a factor of j to the minus 1/4. So you see, time is running slower for an observer at the endpoint. So this means that if I consider, say, a wave from the bulk to go here, this will appear blue shifted, and this means that the effective cutoff on the energy as measured from an observer here will be smaller than will be effectively smaller due to this blue shift effect as you move here. So the outcome of this, if you think of it, is that the cutoff on observable, which are sensitive on the boundary condition of this endpoint, is roughly the bulk cutoff, which is of course 1 over Ls, divided j to the 1/4. This is of course roughly mg. Okay. So this is not, you might be worried by seeing a cutoff which becomes smaller with j, but you have to remember the typical energy for excitation top of the string goes like 1 over the length of the string. And the length goes like 1 over square root of j. So you still have a huge window of states that you can control in your effective field theory. So the length goes like 1 over the length goes like. You have a huge number of states that you control in your effective field theory at large j, but it's smaller than you would have guessed because of this j to the 1/4 factor. That's the whole physics of this problem. Okay, so in 2 words I'll tell you about the technical implementation. Okay, I think I'm doing okay. Is that argument clear? By the way, I think one point I'm talking about open strings, but I think it's hopefully clear that all I'm saying is really the same for closed strings in terms of these physical arguments. So,
Because closed strings have some sort of cusps.
closed strings have cusps that move close to the speed of light, so this is the reason why they are singular, is really the fact that the cusps move at the speed of light. And once you accept that they will get some mass by this normalization effect, there really are some point particles that you have to, they are like singularity from the viewpoint of the worldsheet metric, so it's like a black hole, so it makes sense to treat it as a point particle like we are doing for this endpoint style. And then the redshift counting applies the same, and this j to the 1/4 is clearly also there. And we also believe that the number of Wilson coefficients you have for closed strings is the same as for open strings, at least to the order we have looked at. But that is still in progress, so I might be saying something wrong. Anyway, we believe that the two problems are one. I think it's widely believed to us very similar. I think we believe that all we are saying should apply almost verbatim, also the technical level.
Also, sorry, just to understand that.
Yes.
So you introduce a delta, some regularization at the endpoints to.
I didn't tell you to do that in practice. That was the physics picture.
Okay. So is this cutoff associated to that one, by the way? No.
So a priori, okay. So roughly speaking, of course, this object will have a thickness which is lambda QCD. But the point is that in a sense you need 2 regulators to do calculation. One for quantum correction in the bulk, and one for this endpoint singularity. So a priori you can do 2 independent RG.
Okay. In this last claim was also some relation between even the cutoff at the bulk changes depending on how far.
So I would say, so if you do a measurement locally around the center of the string, your cutoff is lambda QCD. There is nothing.
Okay.
If you want to compute something which depends on the boundary condition of the endpoints, the cutoff is lower by that factor there. So if we are interested in the particle spectrum, so that is the cutoff. It applies for us. If you come up with some inclusive quantity that doesn't depend on this boundary condition, then we will have more control on that. In fact, it would be interesting, but we don't know any interesting quantity, which has this feature. Okay, so the technical implementation in one line.
Can I ask you, for fundamental strings, you don't give this
Yes.
correction?
No.
So what is the picture? What saves? Why it's not appearing there? Is it in terms of the way you presented it?
I mean,
I couldn't hear the question. Can you
It's not that for fundamental strings there is no j to 1/4, and I ask how to think about it.
I think if you just take Nambu-Goto action, you would be happy without never adding boundary terms and never adding higher bulk terms. Classically, quantum level, you're happy only equal to 6, and you never see the need of adding those terms. But I don't know. I mean, I guess it's in principle possible to have some endpoints. To imagine modifying with some interesting. Well,
For fundamental string, the picture is that it actually moves with the speed of light, and there is actually singularity, but you solve the theory exactly, so you kind of...
Yeah, that's trying to wonder whether you can modify the fundamental string in a consistent way with the endpoints now moving slower than the
One way you can have it is that if you have fundamental string and ADS, you have one vertical, and then you effectively induce some massive.
Yeah, in ADS, I got it, yeah. So, okay, let me just tell you where we implement this conceptual program. Okay, so this is the action we write. Tau x squared on tau minus 3. Yes, let me just tell you what is that plus so let me just say what it is. Yeah, sorry, maybe I'm going to many details, but I thought I wanted to say something about what we do. Okay, so let me just flash this. Maybe it's too much detail, but since, again, some of you heard this from Sergei, I'd like to explain this in slightly more detail. The way we implement this is we write an action in which now you can argue pretty fast that the only operators you should write at the endpoints are just time derivatives of x. And we write an effective endpoint metric which is given by the square root of the acceleration. So this is a very singular thing to do for a point particle, but it's not singular here because you should remember we're expanding on a background where the endpoints are spinning very fast. The acceleration is never a singular object. And then we write higher derivative terms in a rather straightforward way. So you have higher derivative terms in x suppressed by this metric. The powers of gamma tau tau are all dictated by reparameterization invariance in tau, which is nothing but a convenient way to impose the nonlinear realized Lorentz invariance once you reach fixed. And the claim is that to the first subleading order, we just have one operator here, which is the j to the 1/4, and one operator here, which is the j to the minus 1/4. So the power counting, let me just say how it goes. And neglect for a moment this as rag. I'll tell you what it is in a moment. So since I work with dimensionless x and dimensionless the coordinates, all I need to do to power count is to power count really the powers of the metric because derivatives are dimensionless. In the bulk, the metric stays like length square, as you would guess. And in the boundary, we have this effective metric, in which case like ls over omega. That's the claim, and you can verify it. So this means that the Nambu-Goto term goes like j. Remember in relation that this is like j. This goes like j to the 1/4, and these terms contribute to the j to the minus 1/4. So it means that to relative j to the minus 5/4 order, for whatever observables, I just need these two coefficients. And these are way more important than bulk higher derivative correction. Bulk higher derivative corrections will contribute to 1 over j. So you might be a bit sad about this because one point was probably understanding whether the bulk higher derivative correction that people measure on the lattice could be used for a particle spectrum, but they enter a very subleading order in this expansion.
Sorry, and why? What happened with this argument?
So the fact, so this, you see, So the relative difference between this and this is not 1 over the length square, as you would expect. There would be 1 over j. It's 1 over the length square with that redshift factor. So the 1 over square root of j. So the expansion in the bulk goes in powers of 1 over j. Here the expansion goes in powers of 1 over square root of j, and that's physically due to this redshift factor. The way we implemented it is using this method here.
No, I was just asking in practice what happens if you take, say, this curvature to the fourth.
I'll say in 1 second. So there is something that I didn't explain that I was using a regulator delta. How do I implement it? Well, the problem is that in the string, the size of the endpoint, which is essentially the point where I cut off my bar string, is determined by the equation of motion. So I cannot set, oh, my string is length this minus this. That follows from the equation of motion. So the idea is to use an operator redundancy. So this is the only technical bit. So from the leading order action, which I argue is Namugoto, it follows that at leading order, the velocity of the endpoint is the speed of light plus small correction. So x dot square is 0. So this means that the standard mass term with square root of x dot square is a redundant operator. I can remove it in effective field theory via field redefinitions. The trick here is that the length of the string, which is what I want to cut off, is not an object which is invariant under field redefinition. And it goes like 2 over omega minus a correction which depends on this mreg. Okay, some power here. So essentially, by adding a redundant operator, I don't change anything of my physics. I just change my Wilson coefficient would be now this gamma b1 plus correction proportion to this mreg. I still have 2 because this is redundant. But the length of the string depends at leading order only on this coefficient. I chose the action appropriately to believe me on this technical step. This might seem like a very technical point, but I think it's one of our improvements I like to highlight compared to the former literature, because things Kim proposed before, it wasn't really clear how to apply them for calculation beyond the leading radial trajectory, at least to us. Anyway, this is a very technical point. If you haven't thought about this problem, you can probably believe me. Okay. And okay, so I'll show quickly some results, I guess. But let me first ask for a Victor question. Okay, I'll show the results in a moment. But the claim is that if I now compute a correction to the both leading and daughter radial trajectory, so to the particle spectrum up to this order, they will depend only on this coefficient b gamma and b1 up to factors proportional to this guy, which are always the same in all of them, that vanishes in the limit in which I send this regulator to 0, if you think of this as a regulator. And if I add an higher derivative term, so my physical Wilson coefficient of b gamma and b1, and if I add an higher derivative terms like d2 sigma k to the 4, schematically with some coefficient c4. Okay, so yeah, this is not understandable. So let's add this. Then my physical Wilson coefficient are just renormalized, as I was saying before. So if I now add an higher derivative term, I repeat all my calculation to the order j to the minus 5 quarter, I find the same results as without this term. Up to the normalization, this coefficient b gamma and b1, you see an equilibrium proportion to the regulator coefficient in the inverse to the inverse power to 5 alpha and 3 alpha here. So this is an infinite normalization, again, in the limit in which you remove the regulator. So this again justifies thinking of this redundant coefficient as some cutoff in a sense. Again, so the idea, I should say, that this mreg is roughly like delta in these regions. But okay, so this is the implementation, but the physical picture is what we said before. Let me just show some results. So you have question on this? Maybe
The idea that is also true off shell.
So this for on-shell observables, adding that term doesn't change anything. And I think so this is the claim. So
But what about off shell? I guess we want
off-shell,
to.
so that is this term is so if you wanted to measure something like the value of an operator at the boundary, this clearly affects that. Of course, only at the boundary, right? This is a redundancy at the boundary. But the claim is that this is not a physical thing to do because the boundary is solved with some fuzziness. So changing this is like displacing your boundary a bit inside or outside. So there is no observable, I think, that is affected by this that we believe is physically measurable within EFT. Precisely of this picture of the fuzzy boundary.
Yeah, I guess by off shell I mean something that's kind of, you have your classical solution of straight rotating string plus some small perturbations. Yes. But small perturbations I want to keep generic, right? As long as they're somewhere.
Like the spectrum doesn't depend on this. But like, what do you?
Yeah. Let's say. How do we argue that for all low-lying excited states, all these bulk operators can be, leading effect of all these bulk operators can be reproduced just by changing these coefficients b gamma and b1. Is there an argument for that?
I'm not really showing. So there is a very formal argument that, again, changing this guy is like changing the length of the string, so changing this alpha f, which is somewhat equivalent to, taking a small chunk of that integration on the worksheet and adding that to your boundary. If you use the equation of motion to redefine operator, you see that on the nose you land on this class of operators that we're using. But it's very formal, I don't think we don't know how to push it at a quantitative level, unfortunately. So we have qualitative arguments of this sort, such already Simon had them in his paper that is work. So, but then the non-trivial check we did is that by adding a bunch of these and doing different calculation, these things will out. This is, I would say, way more non-trivial. But yeah, I agree that. Okay, so let me just show some results quickly, and then let me go very quickly to the data, which is the most interesting part. Okay, so the leading ledger trajectory already showed. Sorry for taking so long. I think something like 2 Newton. Is minus square root of 2.
I'm confused. I would think that the first correction to linear should be always negative.
Great, so in this formalism, we are confused for a while. In this formalism, why is this coefficient should always be positive if you think of this as coming from a master? I think that's what you're saying. I think that's what you proved, actually.
Yeah.
So, in the fall, what we are doing, since it's associated to some crazy boundary term that is decoupled from the master, it's by far not apparent this should be positive. In fact, we can have negative coefficient and a perfectly consistent effective field theory, perfectly subluminal, as far as we understand. So, but we know that it should be positive thanks to your paper with Amit. So, I think that, and that shows actually in your paper, well, the ultimate paper even more. What should the positivity thing that you proved there from the bootstrap didn't follow from effective field theory. So we know that this coefficient, so the coefficient here mu1 and mu2 are just some big gamma and b1 up to correction of the regulator that vanish in the limit in which the regulator goes to 0, or renormalizations. And as Sasha was asking, this coefficient, we know it has to be positive. It's not obvious from effective field theory, but it follows from the bootstrap analysis of the S matrix in the Regge limit, which is also controlled by the same effective field theory. Okay. Sorry, this is. So the automated trajectories are just obtained by exciting some harmonic oscillators on the string. So in the case of d equal 4, there are two transverse oscillations. One is an angular one is a transverse one. And okay, it's not really worth going too much into detail. These are the occupation numbers. So this is just a Fock space formula. The only thing I want you to appreciate is that here this sum starts from modes with momentum equal 2, not 1 or 0. This is not because I'm crazy and I like to count from k equal 2. It's because we want to look at the spectrum of physical particles, so we have to mode out by action of symmetry generators and mode out by particles that live in the same spin-J representation of the leading radio trajectory. Turns out that's enough to restrict to modes in this quantization, which are 2 or larger momentum. This will come back in a moment. And as an illustration, just the energy, say, for one of these is omega k, say for this at the ring order. This is like, if you sum that, and remember it's like 1 over square root of j, this is the usual integer space vector for the mass square of this order. And then we can compute the correction, and they depend on the same coefficient. Let me just write the first one for illustration. K squared minus 1. And then here the correction, we computed it. The important point is it goes like k to the 4 omega to the 5 in units. So, okay, so the leading radio trajectory, the M there is a correction which is like j to the 0, which is a quantum effect. Comes from, as you are familiar always with from fundamental string theory, it turns out it's the same in effective field theory. And in this term, the first correction goes like, indeed, this is like j to the minus 3/4 correction. This is like j to the minus 5/4. And the important thing is that by comparing this and this, you see that your effective field theory breaks down when the momentum of the string mode, which is omega k, becomes of order of the endpoint cutoff that I got sometime before. So if you were just thinking of bulk effective field theory, you would have guessed here a much higher power of omega. That's what I'm saying. Omega 7/2. Instead, the relative power is just an omega power. So it's like the cutoff is this factor we showed before. And then, since this is an important conclusion, let me write it down maybe. Lambda endpoint, which is so maybe you would have put a 1 over ls here, instead you're reduced by this factor square root of omega, which means k of order j to the 1/4 in terms of dimensionless number. Yes. Okay, so are there questions on this technical part? Okay. So, you have a question?
So often these large J expansions tend to be quite good at low J even, maybe somewhat surprisingly.
That's what I was.
Okay.
It's less good than what you Okay, so even if you slept until now, you don't care about effective field theories, you might want to wake up for the last 10 minutes because I think there is something more interesting, maybe or newer. Okay, good. So that part of
The second screen is not working.
I think he just wanted to.
if you want, we can have two. If you want, I don't know.
No. If everyone can see this.
Everyone can see that? Yeah. Okay, so we've done all this exercise. We believe we understand effective field theory for open strings. We are working on the details of the closed strings, but so far everything seems to work in the same way. But of course, the real point why we're doing all this is because we want to look at data. And we have slightly more closer detail than what was done in the past. So the first thing we will do is look at closed string data. This is part of an old story, but we have a newer understanding. Old, but not so old. So I told you about open strings, so I'll tell you about closed strings. I'll have to make some assumption, but it's not important. So the motivation, this is actually an old work by Sergey and Guzman that started doing this, of looking at closed string data in 3D was at first to understand qualitatively the global spectrum in terms of quantum numbers of an excited string. So rather than doing the quark model, rather than doing phenomenology, we have a Hilbert space that we obtain quantizing the effective string theory, and can we at least qualitatively understand, if not quantitatively, which of the globals mentioned on the lattice can be assigned to which excitation of the string. And the reason why there is some optimism in this is that because, as I mentioned at the introduction, lattice shows strong evidence that all the excitation of a long string in 3D Yang-Mills are really well described by a single mode, which is roughly interpreted as the transverse oscillation of the string. So we might think that by naively extrapolating effective field theory, if not quantitatively, at least qualitatively, we should be able to understand this pattern. That's the question. To do that, we need to make some assumptions. The first assumption, there is no way around it, and you're probably right to complain about it, but they figure it out and it seems to work, is that when you quantize the leading order free action for the string, so the non-Bogotto action, you obtain some degeneracies, and you assume that these, even at small j, are only weakly broken. This assumption might work or not work, but you need it because otherwise you don't know how to disentangle the spectrum. And it kind of works, and we are going to have to go with that. The second assumption just comes because I didn't describe the closed string Hilbert space for you. I'm very happy to talk about it more offline. But for the level of the comment I want to take, I'll just say that closed strings are nothing but two open strings, square, plus level matching. So I think that's something you all know from fundamental string theory. The difference between closed and open string, when you do Polyakov quantization, is that you have to impose that the momentum around the string is zero. So you just have two sets of harmonic oscillators, and you impose that this level matching condition. Just this stage of procedure to go from open strings pattern to closed string pattern. And here is where things comes interesting. This assumption you might, I think we want to lift eventually, but for now let me use it. Now you might think that at this stage I have a completely well-defined problem, but I don't, because even when I quantize the open string spectrum, there are different choices when I want to go beyond the EFT. So even if I assume that there is a unique mode of the string, there are several ways to extrapolate EFT beyond its regime. Let me explain what I mean. And to explain what I mean, I think I'm going to discuss the simplest model you can think of, which is two harmonic oscillators. So two harmonic oscillators is an Hamiltonian omega A dagger A, or dagger B, D dagger B. And if you want to write an action, you just do it in this first order formalism. And this is going to be good enough for me because there is a conserved quantum number which mimics my J, which is the particle number of me. Now to tell you why am I telling you all this? I know how to quantize this system. This is standard. You learned this when you were, some of you undergrads have learned recently, but most people probably in your, it's not undergrad, some new high school, but most of you in undergrad, I hope. And you get this Hamiltonian, and the only lesson I want to take from here is that the phase space is obviously R4, and the number of particles that you have with angular momentum J is just given by all the states you can work like this. You have J plus one particle at each J. Of course, but however, the point is that this is not the unique thing you can do. And something that is closer to what we do in effective field theory is something which looks a bit more perverted from this viewpoint, which is to expand A and B around some rotating background, and to parameterize A, therefore, in radial coordinates. So I use some pi, which is kind of a Goldstone boss, and chi, which is a real variable, and B, I replace it with some beta, which is a complex variable. Then my quantization gives me that pi is, of course, obviously conjugate to J, and beta daggers here are the usual canonical pair. And then Hamiltonian is this one. It's omega Ej plus something which depends on beta dagger B. But now I can declare that this is my fundamental system. You know, after all, what I want to do is extrapolate EFT, so I don't know how to extrapolate EFT. And if I do this, if I declare that this system is my fundamental system, I find that the particle spectrum at fixed J is not anymore given by J plus 1 states, but an infinite number of states, because I can interact with beta on the vacuum infinitely many times. Of course, the cheat here is that the canonical transformation bringing me to this, from this pi beta variable to the A and B originally is singular at the origin, so I'm cheating. But the point is that in effective field theory, we only have access to the very low-lying states at large J in a sense. So when I just have access to that, I don't know how to extrapolate, even if I assume that I know my field content. And this has actually a nice topological interpretation by saying that the phase space is not R4 here, but R3 times S1. Okay, so hopefully this point is clear. Okay, so now when we do this ASA, this axionic string arcs as I described before, I have to declare which open string spectrum I use. I'll not go into the detail now on exactly how these two things I told you before happen in terms of the open string spectrum, but now you can easily believe that I have two choices. And turns out, otherwise I wouldn't be discussing this, that this fixed J quantization, which is this kind of phase space with a hole, seems to describe very well the spectrum of 3D Yang-Mills glue balls. So here these are the approximate degeneracies of the electric spectrum, and we go to quantization. These colors are different quantum numbers, so not only J, but also P and C. And it turns out that this phenomenological prescription at this stage reproduces very well all the data from 3D Yang-Mills. In fact, I think Guzman knows better. I think they even predicted the quantum numbers of some particles in this way. So there is strong evidence that this is the right prescription to understand the spectrum, and I think this is suggestive, as it's telling us that maybe one way in which confining strings are different than fundamental strings is in the topology of the phase space is vaguely related. It's a very vague comment, but it's hopefully one that we would like to make sharp. Okay, so now let's look at particles in 4D. Okay, so this is going to be particles in 4D. Okay, let's take a breath. Okay, so the other set of data you want to look at is particles in 4 dimensions, so mesons. And you might naively hope, because these leading edge trajectories are so straight, this is the omega F trajectory in isospin 0, this is the rho A trajectory in isospin 1, that you might be able to quantitatively understand the meson spectrum just based on what I told you so far. So, for instance, at first order, I told you that I started counting from momentum 2, which means quantitatively that just at the leading order you should roughly expect your first excitation up here. That's what you find. So at isospin 1, you already see there are many particles which roughly lie at 1 alpha prime distance rather than 2 alpha prime. Isospin 0, you just cry. And so for a long time, and that's the reason why the paper is not out, this was our fate. So I invite you all to find rationales to look at this data. I'll give you the best we found out so far. We by far believe it's not, we hope that there is something better to do. So the best rationale we found is that, okay, we claim QCD is not larger. Data, so especially as spin 0, are contaminated by molecules between different mesons. I mean, PDG calls everything a meson. These are data from PDG, and everything which is in there is a meson. Could be a glue ball, could be even the sigma, be something. What we want to look is states which are continuously connected in n c to infinity limit to mesons in large N QCD. So one feature of mesons in large N QCD is that they are isospin blind. You should observe the same spectrum for isospin 0, 1 alpha, and 1, up to the double counting at isospin 0 because you have SS bar and UU bar. So we stare at this data and try to identify a subset of data that we hope / believe reliably extrapolate to mesons in large N QCD. And as you see, it's way fewer data. This is just in isospin 1, roughly, what we believe are some of this data. So here the colors again I will not go into the details of this, but they describe the parity and sequence numbers, and we know J. Clearly, J is not very large in the regime where we have data, so quantitative matching is probably we cannot hope for that. But at least we should try to hopefully understand something like this. Just for your orientation, this is the row, and this part here, which is almost massless, is obviously the pion. Okay, good. So how do we understand these states? Okay. Well, I didn't talk about spin today, but quarks at the endpoints of the string have obviously spin. Now, in the regime where the string is spinning, the spin of the quark at the endpoint should also go very fast, which roughly means that in the large J limit, you should expect the spin states of the quark to be very gapped by this Thomas precession phenomenon. But okay, here J is small, and the natural explanation for having states here, here, and here almost degenerate is saying that these are actually coming spin families that are related by the various orientation of the spin of the quarks, and say that the spin forces are very small in this regime, like for atomic physics. So by this logic, you start looking here, and then you say, okay, this is the ground state of the string at orbital momentum 0 and spin 1, and this is spin 0, orbital momentum 0. And I think this we know is the correct interpretation of the pion in the row. And again, P and C quantum number work out. These states also, you organize them in a family of 2 spin and a half particle and a string with orbital angular momentum 1. So we don't see string excitation at this stage. And then you try to do the same thing here. And here actually it comes a puzzle which actually is well known in the QCD phenomenology community and we didn't know about, which by extrapolating this logic, here you should find 4 states, because there are 4 states in the spin family of this leading radio trajectory. But we only find 3. And if you go look at data, also data neglected, you won't find this specific state here, which is the symmetric combination with spin 0 and orbital angular momentum 2. And this calls for a question of interpretation. So, and also this state here, we don't know. A crazier proposal that we have is that what's going on here is that the gap of the spin is going up. So because here the spin partner of the linear trajectory is down, here it's degenerate, so if you just extrapolate this curve, you would expect it to go higher up here. And there is again a theoretical expectation that this is what should happen at large J. So we also have a prediction this is what should happen at large J. Then this state shouldn't be a spin state, but might be the first daughter trajectory that we observed. And then also this will be a daughter trajectory. It has apparently the same quantum numbers to be understood as this pseudo-axion state that Victor and the others found. But it's not the unique interpretation. And the main point here is that to decide which interpretation of the data is the right one at this stage, we really need data up here. So if the spin states really disappeared, here we should find a unique state. If instead we see again the pattern of seeing spin family, at J equal 3, we will find again something more like maybe a unique state or a higher gap. So anyhow, these are just first steps in looking at data. I wouldn't be surprised that the right interpretation of data is completely different. And maybe it's hopeless to do it at this stage, but I just would like to suggest that those of you who like this try and have a look and come up with ideas to understand this data, because it's a shame. This trajectory is so straight. People in the 70s claimed they observed string theory, and then you look here and we don't understand anything from the string theory before. There should be somewhere in between. So, anyway.
These are from the experimental data or from the lattice?
PDJ. This is Mesons in your work.
From the lattice, I know that up to spin 1 there are some large N data.
For Mesons?
Yeah. Up to spin 1.
Honestly, I think so lattice we...
So by Biagio Lucini.
You should tell me more. I don't know. You should tell me this reference,
Yeah. Because then it might be useful at least up to spin 1 to see if you match.
Yeah, if they have more data which are more reliable, that would be actually a good point, yes.
Yeah, they do quenched and...
Doing experiments on the lattice is kind of harder, right? That's why
But they do quenched, right? Because in the large N limit, you know that the fermion loops should be suppressed. So you just build up fermionic operators on the lattice, and you use pure Mills configurations.
Okay, so
But you can also do... Yeah, I don't know if...
I didn't know about it. We should definitely look at that, yeah.
But I'm talking about I'm not a lattice expert, so I don't know, this is like my memories from old papers, but I don't know if Biagio Lucini Corbera, they really do the pure, SU16 or something,
Okay.
full simulations.
Yeah.
So, but I know, I remember because I looked at these papers. Up to spin 1, they have some.
Okay, great. Well, I should say, I mean, this of course, we don't want to look at the global data. We have tons of global data, and then one of the things we're slowly starting to do is to use those things to understand.
Right.
And that's more straightforward. Here is, but again, I think lattice data from Mesons, if they are clean, they could be also. Okay, so sorry if I'm going over time. Some quick summary. I told you about how to treat endpoint singularities in effective string theory, how to do calculation in effective string theory for Mesons. And I also told you something about the phenomenology of 3D globals. Let me just highlight the open questions. This is a workshop. We are looking at closed strings, and I guess the main conceptual question there is how to justify maybe better this weird quantization prescription that I told you produces 3D and mixed data. Also, we want to look at quantitative correction for 3D globals since we have more data. And another fun game you can play, since one is effective field theory, there are a number of observables that live very close to leading wedge trajectories, which are like decay rates from leading wedge state at large j to some smaller j, and they are all dictated by the quark-pion coupling at the endpoint. So this is a straightforward extension by effective field theory. It's the leading 1/n correction to a number of observables. And I guess the main question is what I showed at the end. We have Mesons data. They are more patterned than we thought at the beginning, so it would be great to have some suggestions from the audience. Thank you.
So this data you showed masses, but how narrow are those states?
They are pretty narrow. I mean, with the exception of this, which I think is one of the two is the famous sigma resonance, but seems to appear in all isospin channel in some way. All of them, they are like less than 20% or less. They're pretty narrow.
And are there any experimental prospects to measure, j equals 3? Like, is there some what limits them?
There are many.
People just didn't look. People looked for them. It's hard.
There are many unconfirmed. So, if you look at these plots here, there are points here, but these stars mean that they are unconfirmed. They've been observed either by a unique group. So people are looking at that, but most of these states are really not reliable. I mean, I would say still, even in PDG, they're not reliable.
Experiments, like what? Roughly what?
I don't know. Honestly, I don't know. Yeah, so I think anyhow, this question about the missing spin state is a question also in the quark model. Some experimentalists are looking at definitely, but how feasible it is, I don't know.
With glue, suppose you forget the quarks here and just think about glue.
Yes.
What's the matching with data, lattice state in that case? That is quite clean, right? Even in large n.
I mean, we haven't looked quantitatively at that because we're still doing the calculation for that.
In d equals 3, right? It's pretty good.
Pretty good.
Yeah, maybe you can show again the d equals 3.
I think so, but this is still at the level. Yeah, but so this is like understanding in terms of quantum numbers and approximate degeneracies. Understanding the gap between this and this state from effective field theory, measuring these Wilson coefficients. It hasn't been done yet. We're doing it now, but it's not clear whether the quantitative understanding will be perfect because already the Regis law. It seems like it's not perfectly straight for the linear trajectory. So I think this suggests, in a sense, these cusps are heavier than one would have thought, maybe. That's probably what seems to suggest to us.
Yeah, you related to this puzzle that the slope does not match the string tension?
Yes.
The global slope. You think it can be resolved with this j to the 1/4 correction?
So there is a generalization of this whole construction to heavy quark, which is almost. And there, I mean, they were playing just with the plot, including this, refined construction, this master that counts. Now it's not anymore really. Yeah, you do a slightly defined counting where the mass is allowed to be large. It's really intuitively straightforward. Then you get straight trajectory, which looks pretty straight, but they think they could match better this data. They have some curves. We don't know, but I think the question is whether having a heavier than expected cusp would also match corrections to the daughters. If that were to work out, then I think that would be a plausible explanation, and one would need to understand why the cusp is heavier than one would expect from the effective field theory. Now, how heavy it is, because it's a factor of 4, maybe it's okay, it's a factor of 10, maybe we don't understand why it's heavier.
Just to summarize, so this in 3D at leading order is j to the 1/4. You have one coefficient that gives correction to ground states.
Yes.
And also then to excited states,
Yes.
there was j to the -1/4.
It's all j to the -3/4 suppressed.
Okay, but it's the same, just one coefficient.
Yeah, but I'm saying if you accept that you do an effective filter with heavy quark, there's a generation of this where, the counting is both M and J are large, so that refines a bit, and it's still completely consistent, EFT. I mean, actually, that for some reason, just this radial slope suggests that might work better, but you have to look at the daughters really to see if it's a possible explanation. Yeah, we don't know yet.
Any other questions? No, then let's thank Gabriel again and